Since Cassini accreted onto the planet Saturn just under a year ago, it seems like a good point to just look back briefly at what it's discovered. And I decided not to confine the remarks to the hydrological cycle, but to the climate generally. Before I do that, let me just draw your attention to a forthcoming book that I think may be of interest to many of you, be published at the end of the year by Cambridge. It tries to lay out in parallel the story of how we learned about how the Earth's climate worked, in parallel with studying other planets and speculating about planets around other stars. So if you want to read about Edmund Halley's experiment in evaporation and his upscaling to the Mediterranean, or figure out who first talked about ice albedo feedbacks, or when different classes of model came along, refer you to this. This is the 018 ice core climate record for the Earth with Titan in the background. If you can't wait till the end of the year, the pre-space age part is actually available on Amazon for the price of a 6-pack, but there's no pictures in that one. Anyway, Titan is actually the prototypical exoplanet insofar as it has actually made, basically throughout my career, the transition from an object essentially only of interest to astronomers, it was just a dot in the sky, to a world that we now model with climate models and that geologists study. And in fact, many of the tools, the stock in trade of exoplanet studies, like generating synthetic spectra and fitting to low-res data, and in fact measuring light curves, these were all done with Titan. Just 30 years ago, we discovered Xanadu, the leading-edge bright region, through near-infrared light curves before it was imaged a few years later by Hubble. So many of these methods, cut their teeth on Titan. So you're welcome, exoplanet people. So Cassini was in orbit around Saturn for 13 years. And made many observations of Titan, as you know, something like 125 flybys. Titan's clouds have had a spectrum of morphologies and occurrences. At the South Pole, when Cassini arrived at near southern summer solstice and perihelion, the cloud activity was expected to pick up around the North Pole during northern summer solstice in 2017 and leading up to there. But the build-up was actually a little bit slower than I think many of the models predicted. One, Laura, talked about some of this recently. It seems in the latest work that the pattern of cloud activity and rainfall perhaps with latitude and season is difficult to reproduce unless you invoke a near-surface methane reservoir at high latitudes. And there's also results emerging from the models, again, one Laura is involved, pointing to a slightly different character in terms of intensity of precipitation at low latitudes versus high latitudes. So this is a very exciting field for further research insofar as cloud convection affects us materially here on the Earth, and Titan is a wonderful laboratory to explore that. We have a good methane profile from the Huygens probe. The results have been replicated with some remote observations as well. This is always a great way to catch people out. If somebody says, "Oh, Titan has 2% methane," you say, "No, it's 5% near the surface." And if they say it's 5%, you say, "No, it's at 1.5 in the stratosphere." But this profile is actually very interesting in a comparative climatological sense, in that the tropopause sphincter for water vapor, or rather methane on Titan, is rather loose. It's leaky. So the methane is being photolized and lost to space in much the same way that Venus's was earlier in the solar system and the Earth's will once be in the future. And in fact, the stratospheric methane abundance seems to vary with time and place, as far as some Cassini indications suggest. Cassini's made a dozen or two radio occultation profiles giving us good temperature soundings throughout. I mean, this is something you can't do at Venus because the atmosphere is too thick. The radio waves actually get refracted away from the surface. On Titan, we can do top to bottom soundings, and in particular the stratospheric profile in northern winter has appreciable cooling, and there's all kinds of stuff condensing, as Erica Bath's talk yesterday alluded. We've seen, you can literally see some of these condensation processes in action. There was this odd dipole cloud that appeared around 2010 around the South Pole, and spectral indications are that it's actually hydrogen cyanide. There is a little bit of tropopause and near-surface temperature variation, as one discussed, about 3 Kelvin equator to pole temperature difference. The stratospheric temperature profile, gets smoothed out with the occultation method, but the high-resolution measurements made by the Huygens probe itself show these beautiful gravity waves. I mean, Titan has gravity waves, up the wazoo from the basically 80 kilometers up to orbital altitudes to 1,000 kilometers. As Cassini flew through the upper atmosphere, it's seen these in abundance. Obviously, the thing that caught everyone's attention during the Huygens descent in 2005 was the ample evidence of precipitation in the past forming this river network and these rounded cobbles. We have no indication when it last rained. There are measurements that the probe made that suggest that the near surface was damp. It literally felt damp. It felt cold in terms of how the heat leaked away. There was stuff sweated out by the warm probe and warm components. In fact, we even see some evidence, this is work by Eric Karkoschka, that suggests that maybe actually a little methane dewdrop formed on this camera baffle and dripped down in front of one of the 200 pictures taken on the surface. But because the vapor pressure of methane can be reduced by admixture of involatile ethane, you can't really build a constrained model of evaporation through the porous regolith. So, it could have been damp for 100 years and we wouldn't know. It doesn't mean it rained there recently. But clearly it rained there sometime because there are rounded cobbles and some dampness. The low latitudes in general are covered by these massive sand dunes, the size of the biggest sand dunes on Earth, like in the Namib or Arabian deserts, maybe 150 meters high, hundreds of kilometers long. It doesn't mean that it's dry there all the time, but it's dry there often enough that the sand can be mobile. It took a while to understand why it looked like the dunes indicate sand transport from west to east. It seems that basically what the dunes are reflecting is a very transient eastward flow, or westerlies, that occurs during the equinox season when there are storms. So paradoxically, the dunes are made during the wet periods, because you get, just as in the deserts of the US Southwest, you get haboobs, you get strong outflow from rainstorms, and perhaps more general mixing by convection that is bringing eastwards angular momentum down from higher elevations to give this migration. And that's been something that the models have really helped to elaborate. The Huygens profile showed some boundary layer structure. It turns out actually that this rather uniform spacing, which is basically global, of 3 kilometers between the dunes is controlled by the thickness of the planetary boundary layer. And work by Sébastien Lebonnois and Benjamin Charnay suggests that this feature here, this little knee, may be a seasonal boundary layer that is controlling that dune thickness. The probe showed that the 9 AM diurnal boundary layer was probably growing to about 300 meters altitude. So again, we have some interesting observations of the short-term dynamics. The lakes and seas are one of the most interesting features of Titan. They're extensive in the north, although they still only cover about 1% or 2% of Titan's surface area in total. And we know actually from radar measurements, in fact, how deep some of them are. The Ligeia Mare here is about 160 meters deep. The radar transparency that lets us make that measurement means that Ligeia and in fact Punga and parts of Kraken are very methane rich. We still don't know where all the ethane that should have been produced photochemically has gone. There is a sink somewhere and we don't understand where it is. Possibly it's enclathration, possibly it's somehow sucked up into the haze and ultimately the dune sands. There are some differences in composition. We know that Ontario Lacus in the south is more ethane rich. It's also much smaller and rather sadly sort of drying up, which is probably reflecting Kroll-Milankovitch forcing. Right now the southern summer is shorter and more intense than the north, and that's basically distilling the volatiles over to the northern hemisphere. And 50,000 years ago, these seas may have been empty, and all the liquids may have been in the south. So there's some very interesting parallels with the Martian polar layer terrain and our own glacial cycles. This crenellated coastline with flooded valleys and in fact a canyon system suggests that the lake level, the sea level in the north has been rising in geologically recent time, but there are these bright evaporitic deposits that indicate that probably it's been a reversible process that's flipped many times in Titan's past. We have fields for the modelers now of topography, and I'm working on one with a postdoc, Shannon McKenzie, on thermal inertia, and we should have albedo done soon so the models can take over. Ground-based observations are going to be important in the next decade and a half. Keck, adaptive optics imaging, lets us observe the clouds, but even simple measurements, just disintegrated albedo, in the blue. This is work by Wes Lockwood at Lowell. He's done this for a whole Titan year. And you see it doesn't repeat, which is interesting because Titan seas aren't big enough to have a sort of El Nino heat storage. So there's some there's some memory in the system, or there's something else that is forcing interannual variability. Maybe it's the solar cycle, we don't know. That's another interesting area for the future. We could really use a weather satellite at Titan. Cassini was great, but it was in orbit around Saturn, so most of the time it was further away from Titan than our own moon is from us. But an orbiter is a very straightforward mission to implement, would tell us a lot. Right now, we're in the midst of a Phase A study for NASA. It will decide next year whether to fly this or a comet sample return. It's a relocatable lander called Dragonfly. Several of the team members are here. It could make extended meteorological measurements on the surface, as well as profiling the lower atmosphere and studying the surface in different locations. So I've got some conclusions, but they're sort of boring. So let me just jump to a Huygens quote. We had a nice presentation on the diversity of individuals in this and disciplines in this business. So to the astronomers and climate modelers and geologists, I'd like to add us humble instrument and spacecraft builders who go and try and get some data from the planets to help model. So thanks for your attention.
Are there any questions?
So you mentioned that methane is escaping from Titan, kind of like the moist greenhouse process for an Earth-like planet. I have two questions about that. The first is it photolized and then the hydrogen escapes? And the second is, what's the lifetime of methane on Titan at the current escape rate?
So the photolysis is principally by the UV. There are magnetospheric electrons from Saturn that play a big role in the whole scheme, in that they break the nitrogen bonds. So the Titan's haze is not just hydrocarbons, but it's nitriles as well. It's much more complicated. But yes, the principal effect is the UV, and it breaks the CH bonds, and you get ethane and acetylene and a whole host of heavier organics, and the H2 escapes to space. And probably most of those organics are actually manifested in these sand dunes. There's a global equivalent thickness of tens of meters of carbon deposited here. So it's you have an irreversible carbon cycle within which there is a reversible hydrological cycle involving methane. So you have these sort of nested loops. Oh, I'm sorry, I missed that. So the lifetime of the methane in the atmosphere is about of order 10 million years, give or take. The seas that we can observe are not enough to do basically any more than another 10 million years. They do not solve the problem of why do we see methane on Titan. It should have all been eaten up. So presumably there is a resupply from the deep interior by volcanism or outgassing or whatever.